Probability generating functions. If x is a discrete random variable, then its probability generating function is, so g of c is equal to p of 0 plus p of 1 times z plus p of 2 z square, so on. And in a power series form, it can be, or in a summation form, it can be written as p of x z power x, where x goes from 0 to infinity. Now, in a power series form, we know that g of z can also be written as g of 0 plus g prime 0 times z plus g double prime 0 over 2 factorial z square plus so on. So from here, we see that p of 0, if we compare this equation with the second equation, we see that p of 0 is equal to g of 0. P of 1 is equal to g prime 0. P2 is equal to g double prime 0 over 2 factorial. And the general term would be p of k would be the kth derivative of g over k factorial. So what the probability generating function does is that it contains information in the form of a power series of all the probability values of the discrete random variable. So probability when the variable value is 0, that's equal to the value of the probability generating function at 0, and the probability when the variable is 1, probability of the variable being 1 equals the first derivative of the probability generating function at 0. And similarly, probability that the variable takes the value 2 is g double prime 0 over 2 factorial, and so on. So let's take an example. Probability generating function of Poisson random variable is g of z equals e power lambda z minus 1. And now let's see how we use the derivatives to get different probabilities. So g of 0, so put z is equal to 0, you get e power lambda 0 minus 1. That would be e power negative lambda. Similarly, g of 1, so let's write it again. We have we wrote g of z for Poisson was e power lambda z minus 1. So from here, we see that g of 0 is equal to e power, so you put z is equal to 0, you get e power lambda times 0 minus 1, so e power negative lambda. Similarly, if you get g prime, take the derivative, so the derivative of this is just e power lambda z minus 1, and then by the chain rule, the derivative of lambda z minus lambda, so this power when you expand it is lambda z minus lambda, and the derivative of it with respect to z will just be lambda, because the derivative of lambda z will be lambda and the derivative of negative lambda will be 0. So by chain rule, you multiply it with lambda. And then if you get g prime 0, you have lambda e power negative lambda. Similarly, if you take the second derivative, you will get, so lambda is a constant. The derivative of e power lambda times z minus 1 is e power lambda z minus 1. And then once again, the chain rule gives you another lambda. And then when you substitute z equals 0, you get lambda square e power negative lambda. And now let's relate it to what we discussed. We said that p of 0 is g of 0. So p of 0 is e power negative lambda. And then we said p of 1 is g prime 0. We go here. P of 1 is g prime 0. P of 2 is g double prime 0 over 2 factorial. So p of 1 is lambda e minus lambda. P of 2 is equal to g double prime 0 over 2 factorial equals lambda square e minus lambda over 2 factorial, and so on. So now if we recall, we also know that for Poisson, f of x lambda power x e power negative lambda over x factorial, where lambda is the mean. And we can see from here that f of 0 would be e power negative lambda, because lambda power 0 is 1, 0 factorial is 1, and you just get e power negative lambda. And then you put x equals 1, get f of 1 equals lambda e minus lambda over 1 factorial, that's just 1. And then similarly, f of 2 equals lambda square e power negative lambda over 2 factorial. So these are exactly the probabilities that we got from the probability generating function. So that's a verification that this probability generating function, which we claim that e power lambda z minus 1 is the probability generating function of Poisson, and now we see the verification that that's really the case. And let's do another example. So let's say that example, given the probability generating function, so we are now not told that what distribution this is, we're just given a probability generating function. So let's say this is the function g of z is equal to 1 over 1 minus 3 z minus 1. So we are given this probability generating function, and let's say the question is, given the probability generating function g of z of a random variable x, random variable x find probability x equals 1. Okay. So we know that solution, we know that probability x equals 1, which we have been denoting by p of 1, is basically g prime at 0. So let's take the derivative, g prime z. So to take the derivative, it's convenient to write it like this, 1 minus 3 z minus 1 to the negative 1, and then use the power rule. So be negative 1 minus 3 z minus 1 to the negative 2. And then by the chain rule, the derivative of the inside thing. So the inside thing is 1 minus 3z plus 3. So negative 3z is the only variable term. So the derivative of negative 3z would be negative 3. And so that's equal to 3 over 1 minus 3 times z minus 1 square. And we need it at 0, g prime 0, be 3 over 1 minus 3, 0 minus 1, and whole square. So this would be 3 over, this turns out to be negative 3 times negative 1 is positive 3, so 1 plus 3 is 4. So 3 over 4 squared. So that's 3 over 16. And that is P of 1. P of 1 is G prime 0. And let's say, example, find P of 2 in the above example. Solution. We know that for P of 2, you need the second derivative. So first find G double prime Z. Once again, for that, it's more convenient to look at this form. So you can write it as 3, 1 minus 3, Z minus 1 to the negative 2. You take its derivative, you'll get negative 6. 1 minus 3, Z minus 1 to the negative 3, and then the inside derivative is again negative 3 by the chain rule. So you get G double prime 0 to be 18 over, so once again, when you substitute 0 here, negative 3 times negative 1 is positive 3, so 1 plus 3 is 4. So negative 3 over 4 cube, and 4 cube is 64. So that's what it will be, and then it's 9 over 32. But remember, this is not the answer. We want, so the first derivative at 0 is P of 1, but the second derivative at 0 is not P of 2. Remember, P of 2, according to what we derived, was G double prime 0 over 2 factorial. In general, P of K is G kth derivative at 0 over K factorial. So you don't forget to divide by the 2 factorial. So that'd be 9 over 32 times 2 equals 9 over 64.